Welcome to the lecture on two independent means. In this lecture, we're going to determine whether or not the mean from one sample differs from the mean of another sample. And specifically, we're going to talk about that difference being statistically significant in the way that we've done in the past by looking at p-values and comparing them to alpha. So for this particular test, we are going to run a t-test. And the reason for that is because it is very uncommon to actually know the population standard deviations for both populations. The reality is that when you're actually out there in the world doing statistics, you're not going to have that information. And so we're going to assume that the standard deviation for both populations is unknown, and we're going to use the student's t-distribution. So for our requirements, we need two independent samples. We need to use simple random sampling method. And we need to adhere to some very familiar assumptions about the two populations. One is that if you're going to have a small sample size, then you need to come from a normally distributed population. If you don't have that, that's fine. Just be bigger than 30, or at least 30 in this case, meaning that both samples should be at least 30 if you don't have the assumption of a normal population. And since we're running a t-test, we're going to need to know our degrees of freedom. So in the past, when we did a hypothesis test for a single mean with an unknown standard deviation, the degrees of freedom was really straightforward. It was one less than the sample size, or n-1. This time is a little bit more complicated. We're definitely going to have Excel compute this for us. But just to be extra clear on what all of this notation is, we know that degrees of freedom is going to be denoted df, and we have population 1, we have population 2, and from each population, you are going to have a sample mean. So x bar being the sample mean from x1, or population 1, and similarly, x2 bar being the sample mean from population 2. We're going to have our sample standard deviation from population 1, as we'll have our sample standard deviation from population 2. And then we're also going to have sample size from population 1. And we're going to have our sample size coming from the sample in population 2. It's really important to notice here, for independent means, you do not have to have the same sample size. That's going to come up later when we do matched pairs. And it's a really good telltale way to know, am I doing matched pairs or am I doing independent means? So you don't need N1 and N2 to match for independent means. We're going to compute our test statistic with the following formula. Again, Excel's going to do that for us. And mu1 and mu2, I'll make a point of this in a second, but in general, when you're doing your test, when you're doing your hypothesis test for independent means, you're always going to assume that mu1 is the same as mu2, meaning that there's no difference. So you're going to start with the assumption that there's no difference in the means, and then you're going to test to see if they are different in some way. So if your null hypothesis is the assumption that mu1 is equal to mu2, then the difference between mu1 and mu2 is actually 0. And then numerator just ends up being x1 bar minus x2 bar. But again, Excel handles all this stuff for us. So we have The first example, the average amount of time boys and girls aged 7 to 11 spend playing sports each day is believed to be the same, right? That's kind of exactly what we were just saying here, is believed to be the same. Right, so mu1 would be the average amount of time for boys, and mu2 would be average amount of time for girls. So we can write population 1. This can be boys. And population 2, that can be girls. And for the sake of argument, we're going to live in a gender binary world for this example. All right. So when I talk about X1 bar, that's going to be the sample mean for boys. When I talk about N2, that's going to be the sample size for girls. And so we have all of these here. So I'm just going to put a 1 next to boys and a 2 next to girls. It really doesn't matter how you label them as long as you keep track. So the 9 needs to go with the 2, needs to go with the 0.866. Right? That's all the girls' information. The 16 needs to stay with the 3.2 and the 1.00. That's all the boys' information. So you want to see, is there a difference in the mean amount of time boys and girls aged 7 to 11 play sports each day? So if you're going to set this up, I'm going to rewrite our null hypothesis, which is always going to be the assumption of no difference between the variables, meaning mu1 equals mu2. For the alternative hypothesis, we want to see if there's a difference, meaning I want to test to see whether or not mu1 is not equal to mu2. We're given instructions to test at 5% level of significance. So we know that we're going to have alpha equals 5% or 0.05. And then we have all of our sample data. So let's see if I can kind of label this. This is going to be N2. N1, X2 bar, X1 bar, and this will be S2 and S1, right? So using the notation that we saw earlier. Again, you don't have to have it be that girls are 2 and boys are 1. It could have been flip-flopped. As long as you keep everything straight and together with its population, it should not be an issue. So in order to run this test, we are going to appeal to Excel, as we always do, and we're going to use this data to do it. So what you want to do is you want to go in your module 4 Excel, you're going to want to go to the tab that says 2 independent means. And let me actually expand this really quickly just to show you a run around of the Excel page. You have kind of a little bit more going on than usual. On the left-hand side, you have a place to enter raw data. And I'm going to show you an example of that at the end of this video. That'll be our last example. In the main top part, you have sample mean, standard deviation, and sample size. That's from data. So if you were to put raw data in here, so like let's say 1, 2, 3, and you had 4, 5, 6, 7, you can see that it automatically fill out your sample mean, your sample standard deviation, and your sample size. And it would do some computations. If you do not have an alpha, it'll give you a number error. Once you put an alpha, behold, you have all the figures that you need. However, if you have raw data and you also then give it given information, so let's say you have a sample mean of 5, a standard deviation of 1, and a sample size of 10, all of a sudden you're going to notice that you're getting these errors again. And you can always check to be what the error is by looking at what it says here. This is saying data overlap. It's saying like, hey, you are trying to use 2 sets of data. Please don't do that. So for this example, we want to just use data from given information. And that's what we're going to do. So in particular, you want to use this entry area over here. So for our population 1 can be boys. We're going to have a sample mean for boys of 3.2. We have a sample standard deviation for boys of 1.0. And then our sample size for the boys was 16. And again, it doesn't matter what order you put this in, as long as you set up your alternative correctly based on how you've labeled your populations and samples. Okay, so the other sample was sample mean was 2 for the girls. Sample standard deviation was 0.866, and then sample size 9. So what we have is a bunch of output, and we have our alpha at the correct percentage. Let's see, let me just grab all this. So what I want to do is grab all this business and then we can digest it. All right, so this is the same information on Excel, just copied and pasted in the context of the question. We're going to automatically compute our test statistic, which was 3.14239. And it'll also compute a confidence interval for you. You don't need that to answer this type of question, depending on how mom is asking it. But basically, you're looking at, was 0 in our confidence interval? No, okay, that's a bit suspicious. So we're probably going to end up rejecting. And that is true. That's not the normal way that we do it, but just in there for grins, just kind of very loose hand wavy talk about confidence intervals again. Notice that when alpha was 0.05, our confidence interval was 95%, right? Because we know that alpha plus our confidence level has to equal 100%. So if you want to change the confidence interval, change alpha. Okay, what we're really going to be looking at in particular is our p-value. So given all this information, we crank out our degrees of freedom, our t, our standard error, confidence interval, and all that's all nice and cute, whatever. How do I answer this question, right? So remember that you want to first say, hey, am I doing a left tail, a right tail, or a two tail? And the way that you do that is you look at your structure of the alternative hypothesis. So this is telling us this is a two tail test, meaning that if I'm going to appeal to my p-value, I really need to be looking at this p-value right here. And once we have our p-value, we can compare it to alpha. So you have your p-value, you have alpha. Alpha was given as 5%, and our p-value here is 0.005, etc. So clearly p is less than alpha, and we know that this leads us to reject the null hypothesis. So we're rejecting the idea that there's no difference between the variables. And we're saying, hey, based on our sample and the data that we got, we actually have evidence to suggest or support the claim that there is a statistically significant difference in the mean amount of time that boys and girls age 7 to 11 play sports each day. All right, so the next example is going to be pretty similar. The alternative hypothesis will be structured slightly differently. So let's create some space here. So we can organize the problem and its information. A study is done by a community group in 2 neighboring colleges to determine which one graduates students with more math classes. So first, we're given information about College A. So I'm going to actually go ahead and call this Population A. And Population A, I should be getting a sample mean, a sample standard deviation, and a sample size. So College A samples 11 graduates. That's my sample size for A. Their average is 4 math classes. So that's XA bar. And it says the standard deviation for that sample is 1.5. Okay, and then I'm going to repeat the process for population B. So their average was 3.5. They sampled 9 people, and their standard deviation was 1. I'll put 1.0. Here's the kicker. Here's how we're going to set up our HA. The community group believes that a student who graduates from A has taken more math classes. So we know that the null hypothesis is always set up like this. So mu A or mu one or mu whatever, right? That there's no difference. The null hypothesis is always that there's no difference. Then for the alternative, you want to test to see that A has taken more. So you're thinking that mu A is greater than mu B. So this is telling you that you have a right tail test. Right, so the alternative hypothesis is really important for us because it helps us determine how or which p-value we're going to look at. All right, so now that we have all that, we're actually ready to jump into Excel, put it in and see what gets spit out. Oh, one more thing. Alpha is 1% this time. All right, so let's put it in Excel and see what we get. So once I put in my data into Excel, I just want to reiterate that you cannot have any data over here. So once I do that, you're going to get this error. It's going to say data overlap. So if you're getting data overlap error, make sure you only have either raw data on the left or given data on the right. You don't want to have both. So this is what we ended up with. Let's go put that back into our OneNote and digest it. So we know we're looking at we know we're looking at a right-tailed test. Okay, so our right-tailed test for our p-value is here. So what that means for us is we're just going to compare it against alpha. So we can already see that our right tail p-value is a bit high, just under 20%. So it's not looking good. Alpha is 1%, our p-value is 19.30%. So obviously our p-value is bigger, hence we are going to fail to reject the null hypothesis, meaning that we don't have enough evidence to support the claim that College A has taken more math classes. Right now, we're kind of in this place where we can't really say that the variables have a statistically significant difference. So one thing you could notice actually is that if you look at the confidence interval, it goes from negative 1.1282 to 2.1282, meaning that it captures the zero. And since we've captured the zero, we can't rule it out. So if your confidence interval misses the zero, you're going to end up rejecting the null hypothesis. If your confidence interval catches the zero, then you're going to end up failing to reject. Again, this is not the standard way that we normally make decisions for hypothesis testing. However, it's just a fun throwback to confidence intervals that we saw in module 3. To be safe and sure, just go with the p-value. All right, so the last example is going to be, what do we do with raw data? So if we're going to test the claim about mean GPAs of night students and the mean GPA of day students, and we're given raw data, we're going to need to compute our sample mean, our sample standard deviation, and our sample size from each set of raw data. So I'm going to go ahead and throw this into Excel. In MOM, whatever is randomly generated for you, you can actually copy and paste that. So here's what it looks like to put in the data from this problem. So with splitting screen real quickly. You can see that we have the data from Excel, and then it matches the data that we have from the MOM problem. And even though MOM tells you oh, you have 23 night students and 28 day students, that's great. It'll tell you here as well in Excel, so you can always double check. One thing that you want to make sure of is that you have cleared your data out of the given data. So if you have given data from a previous problem, it's going to say data overlap, and give you all these errors. So just clear that out and make sure you're using only one area of input at a time. All right. We also need to, just to kind of clarify where we're at, for our night, which I'm just going to call population 1, we have our sample mean, which is 3.326957. I'm getting that from Excel. And then for our day, which I'm going to call population 2, our sample mean is 3.046071. And similarly, I can get a sample standard deviation of 0.228879. And the sample standard deviation from our day students, and then N1 was 23, N2 was 28. And this matches what's given above in the statement for the question, which is great. So we know that alpha should be 0.01, which is 1%. We know to always use the assumption of no difference between the variables in our null hypothesis. And for our alternative hypothesis, we have to actually read the question to see how we're going to set that up. We know that it has to be HA mu1, mu2, but it's our job to determine, are we using greater than, less than, or not equal to, right? That's for us to decide. So the way that we do that is we just kind of read and get context. We want to test, it says in the first sentence, you are testing the claim that the mean GPA of night students is different from the mean of the day students. So that means we're just using our old friend not equals to. And since we're using not equals to, that tells us that we are having a two-tail test. Well, let me grab the spit out information from Excel. I want to put in 0.01. I need that in order to do this confidence interval and a few other things over here. So now we can see that if we're looking at our two-tail p-value, that we're going to get a 0.00097, and we're comparing that to 0.01. So you have your p-value 0.00097, and that's certainly less than alpha, which is 0.01. So you're going to reject the null hypothesis. You have enough evidence to support the claim that the GPAs between night and day students is statistically significant, that it is different. So again, notice your confidence interval does not contain 0. It goes from 0.067 up to 0.49. So 0 is not in there. Again, a throwback to confidence intervals in module 3. We didn't capture the 0, so we're going to reject.